So lecture number 8, today we're going to be talking about an introduction to game theory. And as part of that, we'll be looking at something called matrix games. And then at the end, I'll be talking about Nash equilibria. And what we'll see is in the next lecture, when I talk about the minimax algorithm, this is going to relate to this. So game theory, technically not usually considered in the realm of AI, but it's all related, and it sort of tells the full story of how we get to those algorithms that are going to do really cool things for us when it comes to multiplayer type competitive games. But first, I sent out a D2L and Discord message about playing this game where everyone in the class secretly chose a number between 1 and 100. So just hand up if you replied to that. So this was the most responded to survey that I've ever done. So the previous record was 40, and I looked at the results about an hour and a half ago, and there were 50, and maybe even a couple of more since then. So thank you very much. It's always great to have more data. And so this game is interesting. So you were supposed to secretly choose a number between 1 and 100. Secretly just meaning that you didn't discuss it with anyone else in the class. And then what we're going to do is, of those numbers that are chosen, I calculate the average of those numbers, so you all know what the average is. If everyone chose 50, the average would be 50, right? And then the winner was going to be the person closest to 2/3 of the average of the number chosen. And so that's what makes this kind of an interesting game, is how you think to play this game. And so here were the results. And there's no prize for this, just like, you know, street cred if you want to brag that you chose the right number. There were 50 responses to that when I chose, which is like 80% of the class. So that's awesome. It's really nice to see people care and take a few seconds to fill that out. So here's the histogram for that. So mostly lower numbers chosen, which is good. The average was 33.8. And so 2/3 of that average was 22.5. And so the winner, if I had to choose, well, 2 people chose 22 and 1 person chose 23. And so 2/3, you know, it's 22.5. So I would consider all of those people winners. There were also a number of people, as you can see, that actually chose between 20 and 25. That's not to say that you, like, everybody's a winner for having participated, right? We're going to talk about this game a little bit and see some of the game theoretic properties of it. But who chose a number between 20 and 25? Okay, yeah, so why did you choose that number? Why?
So I thought, like, if an average is 50, like if everybody chooses a certain thing,
Okay.
and if the number is 50, then 2/3 of that would be 33 point something, right?
Okay.
And I thought, like, maybe everybody else is also thinking the same thing.
Yep.
So they will also choose 30 point.
So you're just...
I again 33.3.
Okay. So just to repeat that for the microphone, because it's not recorded, it's something like, okay, you made some assumption about the average, and then you said, okay, 2/3 of that, and then maybe other people were thinking like this, etc. So that's a chain of logic. Did anyone else who chose, anyone else want to explain why they chose their number? Maybe it was your birthday or whatever in the back there.
Exactly for the same reason. I thought that
Okay.
I would be 2/3 of the 45 and 20.
Okay. So pretty much, like you said, pretty much the same reason. Anyone have any different logic for choosing their number? Again, there's no wrong answer. It's just like, it's interesting to hear why people choose those numbers. Just hand up, remember. Yeah.
I'm not sure. I figured for some reason that people might want to choose higher for some reason.
Okay. So again, the reasoning is some sort of assumption about what other people will do, and then apply some sort of logic to that. Did you have a question, or was that just a... Okay. All right. So I'll get back to that a little bit later. I just wanted to present the results of that so you can think about it. But first, let's talk a little bit about game theory and decision making within that space. So this is game theory is essentially mathematical models for decision making in lots of different contexts. And so it's an analysis of strategic actions in scenarios which we can define as games. And we'll see how we define those games in a little bit. It has many, many uses in social sciences, computer science, mathematics, economics, and everyday life. And in fact, the field of game theory actually came out of economics and economic decision making. So that's where it comes from. And just to give some credit, a lot of the slides in this lecture I actually based on a lecture that I watched from an economics class on game theory. So that was it was nice that I had something to go on. And one of the things that I think is really interesting is that nobody really explicitly teaches you strategies for decision making, right? They tell you, okay, don't touch a hot stove, or don't get in the van with the stranger, or don't take the drugs, or whatever. But like, there's not a lot of like logic around like mathematics of why we make those decisions. So hopefully, after this lecture, we'll have just a little bit more of an algorithm to go on when making certain types of decisions in the future. Okay, so here's another game. And just keep in mind that all of the values that I'm choosing for these games are completely arbitrary, right? I'm sort of telling a story to get numbers on the screen so then we can apply an algorithm to it. But a lot of these things are completely arbitrary choices of numbers. So here's what the grades game is. Two players secretly and simultaneously make a choice. And so a lot of these games, you're not really colluding with the other player, you're just making a choice. And we're going to have a defined outcome based on those choices. And I'm going to label the choices choice alpha or choice beta. This could be choice 1 or choice 2 or X or Y or up or down, doesn't really matter. This is just a label that I'm assigning to the choices. And so here's the outcomes of this particular instance of the grades game. So if you choose alpha, picture you're playing this game with someone else in the class who I've chosen at random. You may know who it is, you may not know who it is. If you choose alpha and they choose alpha, you get a B minus, okay? If you choose alpha and they choose beta, you get an A, so a little bit of a better outcome there. If you choose if you choose beta and they choose alpha, you get a C. And if you choose beta and they choose beta, you get a B+. So just think about that for a little bit, and then put your hand up if you want to tell me what you would choose. And trust me, this is not a trick question. There are literally no wrong answers at this point, because we haven't talked about any of the rest of the process. So in the front here.
Alpha seems the safest option.
So safest, can you define safest a little bit better?
If the other person choose alpha, I will still be better than, like, if I chose beta, I'll be worse. The only case I'm better is the last one.
Okay, so it's talking about like better or worse between the two cases.
Yeah.
Yeah.
The average, the alpha is better.
Okay, average alpha is better. Someone else here had a choice? Yep. Yep. Why is that? Sorry, can you say that a bit louder? Okay, so the chances of you getting an A is higher with alpha because there's no A down here. Anyone else have another choice they might take in the back?
Just the average rating overall is higher as long as you choose alpha.
Okay, so everyone is sort of thinking in terms of averages here. So that's good that we're looking at that sort of thing. All right. So one of the issues with a game like this is that when you define the game and you describe the game in terms of just English description with lots of text, this is actually kind of hard to keep in your head, to view it at one glance, right? So what we're going to do is we're going to take this game and we're just going to write the outcomes and the choices in a table. And so because this is a table or a 2D array, this is a matrix. And so this is the matrix form of this game. It's just that we can write down, okay, so these are the choices that I have. I can either choose alpha or beta. My partner in this game can either choose alpha or beta. And if we both choose alpha, I get a B minus. If I choose alpha and they choose beta, I get an A. If I choose beta and they choose alpha, I get a C. But if they choose beta, I get a B+, right? So this is just a little bit of an easier way of writing down that sort of English long form description of that. And this is what I mean by a matrix game, where the outcomes of that game are in this matrix. And also, so these are my grades here that I would receive, but of course your partner is also playing this game and you're making a choice together. So if I wanted to write down a matrix for my partner's grades, outcomes in this game? Well, it's essentially, if we both choose alpha, we both choose beta, the results are going to be the same for both of us, right? But essentially, this is the transpose of the matrix. So if we take the matrix and we flip it, that's the answers that the partner is going to get, right? Or that's the outcomes for the partner. But having these two matrices, it's kind of your eyes are looking back and forth. It's still a bit hard to parse. So what we're going to do is we're going to take both of these matrices and put them into one matrix. Okay? So this is the matrix that we get. Again, here is my choices, alpha and beta. Here are my partner's choices, alpha and beta. And this is called the outcome matrix. And the things on the left of each cell are going to be the outcomes for the person on the left. And the things on the right of each cell are going to be the outcomes for the person on the top. This is just our representation for this matrix. And here, if I just color code them, if I'm in red, then my outcomes are in red, and if my partner's in blue, then the partner's outcomes are in blue. Okay? So for example, if I asked, okay, if I choose beta and my partner chooses alpha, what's the outcome for the partner? Then you would go, okay, I'm choosing beta, partner's choosing alpha. Then the second one, that would be an A for the partner. So this is how you look at this matrix. It's just a really nice short form for how you can write down and easily retrieve the outcomes in a game like this. So in the grades game, we have actions, strategies, and outcomes. It's not quite a game yet. What might we be missing, right? So what's sort of missing when it comes to, okay, I want to be able to apply some sort of algorithm to this to try and help me make a choice. What's the one last thing we might be missing? What do algorithms usually do? Sorry, just please don't shout it out. Yep. And in what way value? Sure. So one of the things, that is the correct answer, but we call them payoffs, right? So in game theory, a payoff is sort of the objective or the goal of the game. So what does that mean? Well, I mean, what does a B minus mean for me, right? What does a C mean for me? So what I'm going to have to do is I'm going to have to somehow assign numerical outcomes to these. And those numerical outcomes are based on things like, well, how much do I want to have an A versus how much do I want to have a C, right? How much might I care about the partner in this game getting a certain thing, right? So I'm going to have to take this and I'm going to have to assign values to those. But the thing is, this is where most of the trouble lies, okay? So game theory can't help you decide on the objectives or the payoffs. But if you do have payoffs, then game theory can help you achieve your goals, okay? So what this is saying is, the process of taking the actual real-world outcomes and assigning numerical values to those, that is something that you're going to have to do. But once you've done that, these game theory algorithms can help you. So, for example, it might be we only care about our own grade, right? So I might be really greedy. If I got an A and they got a C, I'm just happy because I got an A. That's all I care about. Or maybe later on we'll see, maybe I'd assign a higher value if we both got an A, right? Something like that. But the point here is that we do need this final step of assigning payoffs. So payoffs are assigning numerical value to an outcome. It's basically like, how much do I like the outcome? And the more I desire that outcome, the higher the payoff should be. So for example, imagine one of the players is greedy and just assigns higher payoffs if they do better than their partner, right? So if we both get a B minus, then okay, that's fine. It's not great. It's not terrible. Maybe I assign a 0 to a B minus. But if I got an A and you got a C, then I would really value that as a greedy person because I got more for me, right? So maybe I would say that that's a 3, for example. So if I took this grades game outcome matrix, now I would turn it into this payoff matrix, okay? So for example, if I got a C and you got an A, maybe I would say that's a -1 for me because I don't like getting a C. B minus for both of us, that's okay, but it's pretty neutral. If we got a B plus, okay, that's a little bit better, right? So here I'm just taking grades and I'm sort of assigning numerical values to them. Because once we have numerical values, then we can start the algorithmic decision-making process. Okay, so these numbers here are called utility. And utility is the word in game theory for how much you want something. That is the utility of something. Essentially, how useful is it to you? Players always are going to maximize their utility. So you have assigned payoffs or numerical values to the outcomes, knowing that then you're going to try and maximize these. Okay? So the translation from outcomes to payoffs is very important because you're just trying to maximize those. So in this example, which I've already sort of mentioned, both of us getting a B minus, for me, that would be a 0. It's kind of neutral. Me getting an A, you getting a C, that's really good. In this case, I'm just saying that this person is greedy, right? So if I got an A, it doesn't matter what you get. I just care about my thing. We'll come back to that in a little bit. So in this case, what should you do, right? Should you choose alpha or should you choose beta? And so the algorithm here, actually, does anyone have an answer for that? Would you choose alpha or beta? Just take a second to look at it. There's no right or wrong answer yet. We're about to get to a right or wrong answer. Yeah, in the front. This is how the payoff is defined, right? So these are the numbers. That's fine. If no one has an answer yet, just let me, I can go. So the way we're going to do this in the game theory way is we're going to consider all the possible combinations of choices. Okay, we're going to do this sort of exhaustive search of the matrix. It's not exactly a search algorithm, but it kind of is. So the way we do this, instead of looking first at everything I could do, the way that this is a little easier to understand is to say, okay, what are the things that my partner could do? All right, so let's have a look. So if the partner chooses alpha, all right, so now we're pretending that the partner has chosen alpha. If the partner has chosen alpha, then we have two choices. If we choose alpha, our outcome is 0, right? If we choose beta, then our outcome is -1. Okay, so if they chose alpha, if we knew they were going to choose alpha, then we would choose alpha, right? Because that's the best thing we can do if they choose that. Let's have a look. If they choose beta. If they choose beta, then if I choose alpha, I get 3. If I choose beta, I get 1. So if they choose beta, what's my best choice? It's also alpha, right? So alpha is always the best choice in this particular configuration of numbers, right? Now, of course, there could be no best choice, there could be one best choice, there could be many best choices, but in this case, with these numbers, you can know for certain that you should choose alpha. Why? Because you know that no matter what the opponent does, I keep saying opponent, but it just means other person. Maybe this is a cooperative game, maybe it's not. No matter what the other person does, we have looked at all the possible things that they could do. And in all the possible things that they could do, one of my choices is better than the other choice. Therefore, there's no trickiness, there's no what if, it's just I would always choose alpha if I'm rational, right? If I'm a rational person looking at all the possible choices, I would always choose alpha. So this leads us to a definition. The definition says, we say that a strategy, alpha, strictly dominates a strategy, beta, if my payoff from alpha is strictly greater than that of beta, no matter what the other player does. Okay? So the rule here is do not play a dominated strategy. Right? If something is always a better choice than this thing, never choose that thing. That's the moral of the story here. So the strategy that dominates it is better in every possible case. So let's go have a look again. So in this case, beta is the dominated strategy, right? My choice of beta is dominated by alpha. Why? Because if they choose alpha, my alpha is better than my beta. And if they choose beta, my alpha is better than my beta, okay? So, strategy domination is an often misunderstood term. It does not mean that X is the best choice, right? I've just done an example with only two choices. So yes, if one thing is bad, the other thing is going to be good. But what strategy domination means is that if choice of X is always worse than Y, then X is dominated by Y, okay? We may have X, Y, Z, alpha, beta, gamma. We may have 100 different choices. What strategy domination is saying, it's not that one thing is always the best. It's saying that one thing is always worse than one of the other things. Okay, so just keep that in mind. It's a tricky distinction because oftentimes, just because of the sake of simplicity of examples, we're just using two things. But it means that if X is always worse than Y, then X is dominated by Y. Okay. Another example. Who's heard of the prisoner's dilemma before? You may have heard this example, a couple of people. So the prisoner's dilemma is a often cited example in game theory. And this is a similar type of action choosing game. But here we have two prisoners in separate cells. Now this is not a sort of life lesson in our criminal justice system or anything like that. Again, this is just an example that we've done and put some numbers here. So we have two prisoners that have been caught, some assumed criminals that have been caught on the street by the police, right? The two prisoners have been placed in two separate cells so they can't talk to each other, right? You wouldn't want them to be able to talk about, okay, you got to say this and I got to say this. The police want to separate them so they can question them individually. And what the guards are saying is, okay, you should just say that your friend did it, right? Just admit it. And the outcome of if you admit it or if they admit it or if you don't, that's going to be defined, okay? So here's the outcomes. If neither of you tell on each other, so you're true gangsters, right? Like you never say anything. Neither of you tells on each other. Well, you didn't tell, so you didn't confess. They're pretty sure that they have enough evidence, so they can put you away for a year, but you didn't confess, so they don't have it like absolutely 100%, right? So both of you said nothing, you both go to jail for a year. If both of you tell on each other, then you both go to jail for 2 years, right? Because they have stronger evidence against you. So we got the confession from both of them. They're both going away for 2 years. Now this 2 years could be 5 years, could be 10 years. It doesn't really matter. It's just a number that's higher than one, okay? But here's the interesting thing. If one tells and the other doesn't, the teller is going to go free and the other one is going to go to jail for 5 years, okay? Because they have no evidence on the guy that told, but he knew, and so, okay, you did it, right? And so you did it, they're going to go to jail for 5 years. So if they tell you these rules, what do you pick? That's the choice, right? Does anyone have a choice on what they would pick? Yep.
Tell.
You said tell? Or?
Tell on the other. I would tell.
Okay, why would you tell on the other?
Because it's the dominating strategy.
Well, so that's a good idea to look at these things, but what don't we have yet in this process? The payoffs, right? So yes, we have the outcomes of going to jail for a certain amount of time, but what you have to do before you make a decision, sorry, I wasn't trying to trick you or trick question, like it was a good answer and you actually chose the right thing. But what we need to do is assign values to these outcomes, right? So what we're going to do is I'm just going to assign a linear amount of value to going to jail, okay? Now, in reality, not like going to jail for 1 year is probably worse than half of going to jail for 2 years, if you know what I mean. Like not going to jail at all would be worth like $1 million, right? But what we're doing here is I'm just saying, okay, any amount of time in jail that is a negative value. So you can have negative values here, you can have positive values here, whatever you want, it doesn't matter. But here we have, okay, if they both tell on each other, they both go to jail for 2 years. If they both stay silent, they both go to jail for 1 year. If one tells and one stays silent, then the person who stayed silent goes to jail for 5 years. So let's just pretend like these are the payoffs for this situation. But again, you can now start to think of, oh, this is actually like difficult. How would I assign values to this? Because maybe you would care if your partner went to jail or not, right? So maybe you'd assign more value to you both going for less or whatever. But anyway, these are the numbers that we have, so this is what we're working with. So let's look at, you mentioned strategy domination. Let's have a look at the numbers. So what we're going to do is the same algorithm. Let's look at prisoner 2. Okay, let's pretend that that's the other person. So you're sitting in your cell. They gave you a minute to think about it. And you say, okay, if they tell, right, what will happen if they tell? Well, if I tell, I'm going to get -2. If I stay silent, I'm going to get -5. So if they tell, my best choice is also to tell, right? Okay. Prisoner number 2, if they stay silent, what is my best choice? Well, if I tell, I'm going to get 0, and if I stay silent, I'm going to get -1. Okay? So, ratting out the other person, or telling on the other person, strictly dominates not ratting them out. And now, I'm sure you're all thinking, well, in the actual crime world, becoming a rat has a much more negative payout than this, right? So, if you ever get out of jail, you probably won't have a very good time. But the lesson here is that you have to put that into the payoff matrix, right? So maybe the outcome of you telling has this other later effect that's maybe like minus infinity because you're going to die if you told the police something. But again, this is not, we're not trying to get into real world scenarios. I'm just saying that figuring out the payoffs is hard, but if this was the payoff, then this is the method that we would use to choose that. So in this case, the moral of the prisoner's dilemma, without all these other real world factors in, is that telling on the other person strictly dominates not telling on the other person. I don't know, 10 or 15 years ago, Fox came out with this brilliant game show that was actually, it was literally the prisoner's dilemma. It was called Split or Steal. And on this game, 2 contestants are given 2 balls in front of them. So they open up this container, one of the balls says split and one of the balls says steal, okay? So the drama of this show is that 2 players are sat down and they just talk, and they talk and they talk and they talk. And the outcome of this is that if they both choose split, they each get half the money. So let's say it's $100,000. I think it was either $100,000 or $50,000 or something like that. So if they both choose split, they each get $50,000, if we're using the $100,000 example. If they both choose steal, they both get nothing. If one chooses split and one chooses steal, then the stealer gets everything. Okay? And so again, the drama of the show is they both sit down and they're like, oh, my grandma's sick, she has cancer, my dog only has 1 leg, my kids they can't read, all this kind of stuff, and they just try and convince the other person to choose split. Almost every single person was like, yeah, let's just split, let's just take 50 grand and walk. And the drama is like one person, in this example that I put up here, they put this beautiful woman with this guy who's like single and he falls in love with her. She convinces him to split and then she chooses steal. She takes all the money, right? A real life lesson to us all. No. But this game is just the prisoner's dilemma, right? So if we were to assign values, payoffs to the outcomes of $50,000, whatever, let's just assign linear values, right? Now again, in the real world, maybe, for example, you owe some drug dealer $40,000, right? So getting $50,000 is all you need. You don't really assign more value to having $100,000, right? So again, assigning payoffs is hard, but let's just pretend we assign linear values, okay? So if we look at this game from the point of view of the payoffs being linearly assigned to monetary outcomes, if we both split, we both get half. If we both steal, we both get nothing. If one splits and one steals, the stealer gets 1 and the other person gets 0. Okay, now we can apply some game theory to this. So, is there a best choice? Well, let's look at player 2. Player 2 is the other person. If player 2 chooses split, if we choose split, we get half. If we choose steal, we get 1. Okay, so stealing is better. if they chose steal, if we choose split, we get nothing. And if we choose steal, we get nothing. And so there's a tie over here. So for stealing is better. For stealing, they're both the same. So in this case, we would say that stealing weakly dominates splitting. Okay? Now, again, this is if you assign these payoffs, these numerical values. Maybe the other person is your friend, and you would really like them to get some money or something like that. But again, game theory can't answer that question for you. You have to come up with the numbers. And so this game is solvable, mathematically solvable, right? But the game creates drama by allowing players to talk to each other, try and make a deal. And the interesting thing about it is that they announce up front that you can lie to each other all you want. Nothing that you say or do is legally binding. So if you're like, I swear on my children's life that if you choose split, I will give you $50,000. That is not legally binding. That's the whole point of the show. And I've included a YouTube link here to this clip because it's really funny. So these two guys are on the show, and this guy over here is obviously a mathematician, and he just sits there looking at the other guy. This guy starts talking. He's like, oh yeah, I got this business or whatever it is. He's trying to convince the guy. And this guy just goes, okay, that's cool. I'm going to choose steal. And so you can choose split if you want, and you'll get nothing. And you can choose steal if you want, and we'll both get nothing. Either outcome is fine with me. But I'm going to choose steal. If you choose split, I'm going to get all the money, but I'll give you half. You can believe me or not. But if you choose steal, neither of us is going to get anything. Right? So the other guy is now like, what? Wait, what? Like, don't do that. And the host is like, what are you talking about? And he's just like, yeah, I'm just going to choose steal. He's like, nobody has ever said that before. He's like, yeah, but that's what I'm going to do. So now it's on you. Either we both get nothing, or I get $100,000 and you hope that I'm telling the truth, right? So anyway, spoiler alert, the other guy is like completely defeated. He's like, fine, I'll choose split, and hopefully you give me half the money. And then the big reveal at the end is that he actually chose split, right? And so they both get 50,000. But I think the game like went off the air after that season because they realized kind of how dumb it is, and that's just the best strategy. Is to just go on, say you're going to steal, and the other person decides whether or not you both get nothing or you get something. So anyway, it's just the prisoner's dilemma. It was pretty dramatic. It was interesting. But it's still worth going to watch the video because the crowd goes crazy. Like it's really funny because this is the first time anyone has ever like applied any sort of thought to the show rather than just trying to create drama. Okay, important note, and I've said this already, but I want to say it again. Decision making using game theory assumes that the payoff matrix is accurate for your utility, right? You have to make that decision. So for example, if you get $1 million, that might be not double the value of you getting $500,000, right? Or you might not care as much about beating the opponent or getting a higher payoff. You may care about what the other person gets too. So direct translation from real life prizes or outcomes or prison sentences into payoff matrices values may be difficult, and it oftentimes is quite difficult, okay? So just keep that in mind. Okay, now let's go back to the grades game for a second, and what I'm going to do is all of these matrices that we've seen so far have been symmetric, meaning that whatever I get is the opposite of what you get, right? So they've all been symmetric. So the matrices have all been just transposed of each other. So these are the grades obtained by both players in the grades game. What might a sample payoff matrix look like of different types of players? And what I mean by different types is two people who feel differently about the outcomes. So I'm going to assign maybe different utility than you. Okay, so let's have a look. In the previous example, we were just both like greedy players, right? We only cared about ourselves. We gave neutral values to neutral outcomes, and if I got something more, then I valued that really well. Okay, what if we had someone, I'm going to call this a caring player, where, for example, if I get an A and you get a C, that used to be 3 because I really cared only about my grade, but maybe now that's a -1 because I care about what we both get. right? So the outcome of what we both get is what I'm valuing it on. And if I get a C and you get an A, previously that was -1, but maybe now that's -3 because I'm sort of angry or whatever. I'm a more emotional player maybe. So this is all just dumb pretext to change the numbers, right? But it's sort of an example. So, did I go back or forward? What happened? Okay, so these are the different payoffs. This is what we used to have. Oops. This is what we used to have, and this is the payoff for that caring player. But it's still symmetric because both of these players are caring. So, but let's first do a little bit of analysis on this caring versus caring scenario. Okay, so what if each player cared about each other? So these numbers change in this way. I just went over that. Is there a dominated strategy here? Okay, so we'll apply our algorithm. So for the partner, let's fix the choice of alpha. If we do, then alpha is better than beta for us, right? If we choose beta for the partner, then, oh look, beta is actually better than alpha for us. And so there is no dominated strategy here. And so in any case where there's no dominated strategy, you can't really, the algorithm didn't tell you what to do. And so what we were doing at the beginning of class, sort of looking at either the best case or the worst case or the averages or whatever, this is sort of the thing that we would have to resort to if there was no dominated strategy. So we can look at, for example, oh, maybe in the best case, I'm going to choose beta because if they choose beta, I'll get 1 or something like that. Or in the worst case, well, alpha, alpha has the best worst case, but beta has the best case. There's all sorts of ways that you could think about it. But the point here is that if there's no dominated strategy, we can't for sure tell you what to do using game theory. Okay, now, what if there were mixed players? What if we had one greedy player and one caring player, right? So, will the choice be different if the two players are different? Well, let's have a look. So we'll take the first half of these greedy players and the second half of the caring players, like this, and then we'll form that one matrix, right? So now the matrix is no longer symmetrical because greedy has different payoffs than caring. Okay, so as the greedy player, is there a dominated strategy in this game, right? So let's have a look. If I look at alpha, right? So the caring player chooses alpha. If I choose alpha, that's a 0, which is better than beta, which is -1. If the caring player chooses beta, I'm going to choose alpha. So alpha is also better. So in this case, alpha dominates beta. So beta is always worse than alpha. Okay, so for greedy, alpha is always better than beta. Just remember that. Now we're going to flip it. So now we're playing from the caring person's point of view. So I've flipped things. So now the greedy player is on top, right? So as the caring player, which strategy do I choose? Okay, well, Dave, let's do the same algorithm. Let's get on with it, right? So if the greedy player chooses alpha, I'm going to choose alpha because it's higher. 0 is higher than -3. But if the greedy player chooses beta, then my beta of 1 is higher than -1, right? So there's no domination. So if there's no domination, I just said, hey, game theory tells us if there's no domination, we don't know what to do. However, this is the last case where, what did we just say about the greedy player? Right? For the greedy player, alpha dominates beta, right? So, what is a rational greedy player going to do? Choose alpha. We know they will choose alpha. Therefore, if we know they should choose alpha, then we should choose alpha as a best response to their choice of alpha. Okay? So, the moral of this story is sometimes if I don't know what I should do, look to see at what the other person should do. And if there's an obvious best choice for the other person, let's assume that they make that choice and we choose a best response to that choice. Okay, so that's the moral of the story here. So this is just to introduce the concept of a best response. Oh, by the way, if I'm doing this algorithm 30 times in a lecture, you can believe that that's going to be on the midterm, right? So just this is going to be a midterm question. I'll give that one out. I'll give you a matrix and give you some questions about that matrix. Okay, so a best response is the strategy which performs best against a given other strategy, right? So if we fix their choice, we can choose one of ours to be the best response to that choice. And it's a response because they've already chosen something. In the previous example, we knew that the other player had a best choice, so we choose our best response to it. And Sun Tzu, The Art of War, to know your enemy, you must become your enemy, right? So put yourself in your enemy's shoes and then see what they would do and then assume that they would make the best decision, because if not, then they're a bad player. Okay, more definitions. What makes a game? We've been talking about these games, we've drawn matrices or whatever, but this is the actual definition here. So in these games, this is going to be from the outcome. This is the numbers game. So here I'm describing the numbers game in game theoretical definitions here. So the players, I, J, K, L, M, N, O, P, there's some number of players. We could call them letters or numbers or whatever. Then when it comes to strategies, lowercase s sub I, that is the particular strategy that was chosen by player I. So for example, if you chose number 13, then your S sub I in the numbers game would be 13. If you chose to tell, then S sub I for you would be tell. Okay, that's what that is. Capital S sub I, that is the set of all possible strategies that you had to choose from when you made your decision. So for the numbers game, that's 1 to 100. For the prisoner's dilemma, that's tell or stay silent. Okay? S is a strategy profile. I wrote sheets over here because the first time I gave out the numbers game, I actually had people write it down in class. And so a strategy profile is a mapping from every person in the class to what they actually chose, right? So if I took the big spreadsheet from that Google form where everyone's choice was mapped out to them, that would be the strategy profile. It is an actual playing of the game with a choice by everybody. For the prisoner's dilemma, if I chose tell and you chose tell, that would be a strategy profile, a choice for each of us. And then so S sub I means the choices for everyone but player I. And I'm going to be using this in a definition in a second, so that's why I put it up there like that. And so if there were 100 players in the game and S sub I, where I was me, it would be everyone else's choice except me. That's what S sub I would be. And then the payoffs are going to be lowercase u sub I of S. And S here is the strategy profile. So what that means is that u sub I of S is going to be my payoff given the choices of everyone who made a choice at that particular round of the game. Okay, so for example, it may have been winning $5 or going to jail for 2 years or whatever. And we assume that when we're playing a game, all of these are going to be known values, right? Because if we don't know all these values, then we can't apply game theory to it, okay? So there's the players, there's the strategies, the set of all strategies, and the utilities. That's what we need to know in order to apply these algorithms. And I'll get back to these things in a bit. Let's look at another example. So far, all of our matrices have been 2 by 2, right? It starts to get a little bit trickier, not much, but a little bit trickier when we go to weirdly shaped or bigger matrices. Now, just keep in mind that these players, like there could be an infinite number of players. There could be 100 players. There could be 3 players. But I'm choosing 2 because I can't draw in 3 dimensions or more dimensions on the sheet. So this is like the easiest way for me to describe things, but there could be, just like in the numbers game, there were 50 players, but I can't draw a 50-dimensional matrix here, okay? Okay, so in this game, the players are player 1 and player 2, so players 1 and 2. The strategy sets, S1 is T and B. So I've just assigned some numbers to these, so T and B might be top and bottom, okay? That might be a choice. S2 is going to be LCR, which is left, center, right. Maybe there's some, I don't know, kicking and punching game or fighting game or something like that. The payoffs, so for example, the utility for player 1 of player 1 choosing T and player 2 choosing C is going to be 11, okay? U2 of player 1 choosing B and player 2 choosing L is going to be B, L, U2 is 4, Okay, so on an exam, if I give you this matrix and I say, what's U2 of BR, you'll be able to look that up in the matrix and give it to me. Okay, the question here, does player 1 have a dominated strategy? Look for maybe 30 seconds and put your hand up if you want to answer if player 1 has a dominated strategy. Yep.
Would be T.
Why is that?
The payoff is higher for both. Only the R choice will give him the 0. Other than that, it's 5 and 11.
Okay, did you have another answer? Okay, so in this case, this is where it gets a little bit tricky, right? So it does not have a dominated strategy. Why? Let's have a look. So if I choose L for player 2, then B is best. If I choose C for player 2, then T is best. I don't need to keep going at this point because I've shown that there's no action for player 1 that's always worse than the other action. Right? So that's what I mean by that, is that for player 2, you may have been doing it the other way, like looking at the 3, but that's fine. So does player 2 have a dominated strategy? Meaning, again, it doesn't mean are any of these always better than all the others? It means, is one of these ever better than any of the others? I know it's a bit nerve-wracking to put your hand up in case you're... Okay, let's just do the math. It's fine. But your hesitation here, don't hesitate on the exam. Make sure you just apply the algorithm. Okay? So let's have a look. Now, when you're asking about player 2, the math is sort of reversed, right? So it's a little bit trickier to do. So let's have a look. We're asking about player 2, so now we have to fix player 1's actions. Okay? So if player 1 chooses T, L is going to give me -1, C is going to give me 3, R is going to give me 0. Okay? If player 1 chooses B, L is going to give me 4, C is going to give me 2, and R is going to give me 0. So what we have to do here is we're not saying, is anything always the best? That doesn't matter. That's not what we're asking. We're asking is one thing always worse than another thing? So let's have a look. Is C always worse than L? Well, 3 is better than -1, but 2 is less than 4. So C and L, there's one in the other, right? So no. Is L or R always worse than L? So for R, we've got a 0 and a -1, so R is better. For R and L, for B, we've got 0 and 4, so L is better. So no, R is not always worse than L, or the other way around. Is R always worse than C? 0 is less than 3, 0 is less than 2. So yes, C dominates R. That's the answer here. Okay? So the moral of this story, after we've done all this analysis, is what? Player 2 should never choose R. Perfect. That's the only thing that we can say here. We can't say what they should do, but we do know what they shouldn't do, which is to play a dominated strategy. Why? Because there's something that always does better. And so you would never choose R as player 2, because anytime you would have chosen R, you should have chosen C, because it's always better. But that doesn't say you should always choose C. It only says you should never choose R. So that's a very important point. Okay, what did I have here? Oh yeah, so I just highlighted this here. Okay, so it gets a little bit trickier when we have like weirdly shaped matrices or more than 2 actions, but you should be capable of doing that. So player I's strategy S sub I prime is strictly dominated by player I's strategy S sub I if the utility given S sub I for every other player's actions is strictly greater than the utility of S sub I prime for every other greater action. Okay, so that's how we would mathematically define it using our new definitions. And this just says, hey, if it's always better, no matter what anyone else does, then it's strictly dominated. Okay, here's another game. You're defending a city. You have an army in the city. The attacker has 2 armies. There are 2 entrances to this city, and you can't split up your army. You have to choose, I'm going to defend entrance number 1 or I'm going to defend entrance number 2. There are 2 paths leading into the city, the easy path and the hard path. The easy path is just like a big open field that the attacking army can walk right up to your city. The hard path is like, you know, someone crossing the Alps with a bunch of elephants to attack you or whatever, right? It is very difficult to go through that path. So you can only choose to defend one of the entrances, and those 2 paths, one is the easy path, one is the hard path, and you have to make a choice. If the attacker chooses the hard path, then half of their army is going to die just trying to get through that hard path. So they're going to lose 1 just choosing the hard path. If they choose the easy path, nothing happens. If your armies meet, then your army and one of the attacker's armies cancel out. Okay? So you've defended against one of their armies. And the enemy wants to maximize the number of armies in the city, and you want to minimize the number of armies in the city, which means you want to maximize the number of armies that you kill or destroy or stop from the other person. So here is this, my MS Paint rendering of this. Here's the hard path. You're sort of going through the mountains. If they come through the mountains, they're going to lose half their troops, or they're going to lose one of their 2 armies. If they come through the easy path, then defend this one, right? Okay, let's assign utility to the number of armies stopped for the easy player and the number of armies that reach the city for the hard player. Okay, so the attacker payoff is the number of armies that reach the city. The defender payoff is the number of attacking armies that are killed. Does the defense have a dominated strategy? Well, let's have a look. If the attacker chose the easy path, then if I choose the easy path, I'm going to defeat one of their armies, right? If the attacker chooses the easy path and I chose the hard path, I went to the wrong place, so I defeat none of their armies. Okay, so that's worse for me. So if they were to choose the easy path, it would be better if I chose the easy path. If the attacker instead chooses the hard path, if easy chooses the hard path, then I am going to defeat one of their armies, right? If I choose the I don't defeat one of their armies, but they lose one of their armies coming in, right? So technically one of them is down. But if they choose hard and I choose to defend hard, then I have effectively stopped both of their armies, right? Which is good for me. So does defense have a dominated strategy? Well, if they choose easy, me choosing easy is better. If they choose hard, me choosing hard is better. So no, not immediately. I don't have a dominated strategy. So what did we say? Sun Tzu, right? Become your enemy. Does the attacker have a dominated strategy? Well, now we have to look at the choices for the defender, right? So if the defender were to choose easy, if I choose easy, then none of my armies were lost in the trip, but I lose 1 to the defense. So one of my armies get into the city. If the attacker chose the defender chose hard, and I chose easy, then I just walk right through the gates, right? So this is the best possible scenario for the attacker, right? They want this one if possible. So choosing, in the case of them, this is difficult to all keep in my head. In the case of the defender's choice, it's always better for the attacker to have chosen easy, right? Okay. If instead, I did that completely wrong. I'm sorry. My brain is mush. Okay. If we're talking about the attacker, we have to go across, not down. I went down. That was wrong. You should have told me. Okay. So if the defender chooses easy and I choose easy, then I lose 1 of my armies because they defended correctly. If they chose easy and I chose hard, then only 1 of my armies makes it to the city because I chose hard and I lost 1. Okay. So in the case of the defender choosing easy, then my choice of easy or hard will result in the same thing. Okay. But if the defender chose to defend hard, then if I choose easy, both my armies will make it to the city. If I choose hard, then I lost 1 plus I lose another 1, so I get 0 into the city. Apologies for that slip up, but it just shows how easy it is to make a mistake like that. So easy weakly dominates hard. Why? Because it does the same if they choose easy, but it does better if they choose hard. Okay? So weak domination means that it's greater than or equal to for all of them but one, but it's better for at least one of them. Okay? So for example, if it's the same for 9 different scenarios, but it's better for one, then that's weak domination. It's only strictly dominated if it's always strictly better no matter what. So that's weak domination. So the moral of the story here is you probably, as the attacker, you probably should not play a weakly dominated strategy. Why? Because, well, if it's the same in this one, it doesn't matter. And if it's better in the other one, then choose the one that's better in the other one, right? So if you know the attacker, if for the attacker, hard is weakly dominated, then they probably won't choose hard. They will probably choose easy. So then you should choose to defend easy. Okay, so this is the chain of logic that we're using. So just a recap. So for our players have players, games have players, strategies, and payoffs. They want to maximize their payoff. A strategy dominates another if it is always better, that means strict, or as good, meaning weak. Never choose to play a dominated strategy. And if there is no best strategy to play, consider the other player's choices first. And if they have a best choice, then pick a best response to that. Okay, so now let's go back to the numbers game. In the numbers game, right, are there any dominated strategies in the numbers game? Hand up if you can think if there are any dominated strategies, meaning numbers you shouldn't choose. Yeah, I saw you nod your head. Why is that?
Because that means that everybody would have.
Okay. In front of you, you were nodding a little bit. What was your reasoning? Okay. That's pretty good logic, right? So let's look at that for a little bit. So let's say everyone was as dumb as possible, right? Not dumb, but like let's say everyone chose the maximum number of 100. If everyone chose 100, then the average would be 100. 2/3 of the average would be 67. So that means, if you think about it, choosing 67 is always better than choosing anything higher than 67, right? So you would never choose, sorry to drive this home, you outed yourself though, I didn't ask you. So choosing 84, it would always have been better to have chosen 67, right? So that is domination. These are dominated because this choice was always better than those choices. However, what's coming next? Well, if nobody plays a dominated strategy, then what's the maximum number that anyone's going to choose? Well, that's now 67, right? So if everyone picks the max of 67, the average is 67, and 2/3 of that is now 45. And so once we delete all of them, they all become dominated strategies by 45. And so on and so on and so on and so on, right? And then you keep repeating. You can keep repeating that all the way down to 1 if you want to. However, as human beings, even though this mathematically goes down to 1, will choosing 1 ever win this game? Right? No. So this biases things a little bit. However, this is called a rationality chain. And it's this sort of, standoff where it's like, if I know that you know, that I know, that you know, that I know, like how many of those do you do before you stop and say, okay, I think that person is pretty smart. So they're like 4 levels deep. It's weird. So 68 to 100 become dominated if you're rational, right? And if you're rational and you know that other people are rational, then we take these off, and so on and so forth. And all the way, you know that I know all the way down to 1. So what I want you to think about, oh no, you can't think about that yet because I haven't done the slides on it yet. So don't think about that. But be able to answer questions like this for the exam. Okay. We talked about in the past, this is the slide from before. As the carrying player, which strategy did we choose, right? Nothing dominated other strategies. So we looked at the other player and found that they had a strictly dominated strategy. So the moral was that This is the best you can do given your belief about what the other players are going to do. And this is a best response. A best response is a very important concept, not only for this lecture, but for the future algorithms that we're going to do. Here is a Nash equilibrium. There's a couple of different ways that you can think about a Nash equilibrium, but a Nash equilibrium is a strategy profile, meaning there are choices for everybody. That strategy, so the choice for everybody is a Nash equilibrium if for each player I, their choice is a best response to the other player's choices. Okay? So keep in mind that a Nash equilibrium, it's an equilibrium because it has to do with everybody. It's an assignment of a choice to everybody. So on an exam, if I ask you for a Nash equilibrium for this matrix, you can't say the Nash equilibrium is alpha. That doesn't make any sense, right? The Nash equilibrium would have to be something like player 1 chose alpha, player 2 chose beta, right? If there's 2 players in the game. Okay. Why are Nash equilibria important? Why is everyone best responding to everyone else important? Well, first, there will be no regrets in your choice. So for example, if we hold the strategies of everyone else fixed, no individual player has any strict incentive to deviate or change their strategy. So it means that once everyone has chosen something, if that's a Nash equilibrium, then no single player could ever go back and look at the results and have done better if they chose something else. Okay, and we'll show a matrix example of this in a bit. And it's also self-fulfilling. If everyone believes that everyone else is going to play the Nash equilibrium, then that person should also play the Nash equilibrium. And we'll see why. Here's a Here's a Nash equilibrium example. So what we have to do is calculate if any of these cells in the matrix are both players best responding to each other. Okay? How do we do that? Well, we're going to go row by row and column from column, and we're going to write down what the best response for each player to each other action is. Okay, so let's look at player 1. What is the best response of player 1 to the left action by player 2? Okay? It's 4. It's M. Yeah, and please just put your hand up if you have it. Don't just yell it out. Okay, so that's M. Now I'm going to step through this a little bit quicker, right? Because you're all capable of doing this. What is the best response to C? That's U, because it has this value of 4. What is the best response to R? That's D, because it has the highest value of 6. Now we have to go from the columns, right? What's the best response for player 2 to player 1 choosing up? That's L, because they have the value of 4. So now we're looking at the second values, remember. This is where people get tricked up sometimes. 4 is bigger than 0 is bigger than 3. What is the best response of player 2 to player 1 choosing M? That's going to be C. Sorry, the green is a little bit hard to see. I should change that color. What is the best response of player 2 to player 1 choosing down? That's going to be 6. What is the Nash equilibrium for this matrix? It happens to be down and right. Okay? Because both players are best responding to each other at that cell. Just a quick note about Nash equilibria. There could be no Nash equilibria. The numbers could work out that there is no Nash equilibria. The numbers could work out that there is one Nash equilibria. The numbers could also work out that there are multiple Nash equilibria. Okay? So if I give you a matrix like this on an exam, and I say calculate the Nash equilibria, your answer is either going to be there isn't one, or this is where they are if there is one or more of them. Okay? Now, I said before that nobody has any incentive to deviate from a Nash equilibria. What did that mean? Okay, so let's fix our strategy choice for every player. So player 2 has chosen right, and player 1 has chosen down. We have shown that they are best responding to each other. By definition, if they are best responding to each other, is there a better choice that they could have made? No, because if there was, we would have chosen that one as the best response. So let's just have a look. Is there a better choice that down could have made than choosing down? No, because anything else would have done worse. right? We would have gotten 5 instead of 6. Is there anything, if player 1 had fixed down, is there anything that player 2 could have done better? No, because they would have gotten 5 instead of 6, right? So it means that if you have a Nash equilibria, and then you go look at the values after it all happened and everyone had made a choice, no single player could have done better by choosing anything else. Why? Because by definition, everyone has chosen the best response to someone. Now, that being said, it doesn't mean that the Nash equilibria is always going to give you the highest result, right? But it guarantees that you couldn't have done any better by changing your answer given what everyone else had done. Okay, is this another example? Yeah, let's do another example. So left is going to be M, C is going to be M, R is going to be 8, right? Now we're looking at player 2's best response to player 1 choosing up, so we go across. Oh look, there were actually 2 best responses here. Okay, so there's 2 best responses. Keep that in mind that that's possible. This is the highest one for M, and this is the highest one for D. And so in this one, there happen to be 2 Nash equilibria. Okay, now when I'm saying you couldn't have done any better, let's say, okay, this is a Nash equilibria. What I'm saying is not that there is an outcome somehow that you could have done better or gotten more points, because there obviously is, right? You could have been in this one. But what it's saying is, for player 1, for example, fix the choices of everyone else as if they had made those choices. Now, is there anything that you could have done better? No. Because if we fix the choice of player 2 to be this one, and if there were 100 other players, we fixed their choices, we couldn't have done any better because this is the best response to that thing. Okay? So, what some people will think is I ask you, what is a Nash equilibria? It's the best choice you could make. That is not the correct answer. It's the highest result you could have gotten. That is not the right answer. Okay? A valid answer is, it's a strategy profile where everyone is best responding to each other. Or another valid answer, if you want to be a little bit more in layman's terms, is that if you kept everyone else's actions the same, could you have done any better by moving? Right? So those are exam acceptable answers. But it is not the best thing you could have done, because it only makes sense in context to what the other people have chosen. Okay, when we talk about dominance and Nash equilibria, so here alpha strictly dominates beta. Let's find the Nash equilibria, and this is our original one, our greedy choice. So let's do the best responses. So the best response to alpha is alpha. The best response to beta is also alpha. For player 2, the best response to this alpha is this alpha, because 0 is higher than -1. The best response to my beta is their alpha, because 3 is higher than 0. And so no strictly dominated strategy can ever be played in a Nash equilibria. Okay, so that's good. No strictly dominated strategy could ever be played in the Nash equilibria. And where is the Nash equilibria in this matrix? It's here in the top left. So if I asked you, where's the Nash equilibria? The choice of alpha, that is incorrect. Choosing alpha is the Nash equilibrium. That sentence does not make sense. The sentence that makes sense is that the Nash equilibria is when me chooses alpha and the partner chooses alpha, or alpha alpha, or you point at the cell. It's important that it's choices for both players. More than one Nash equilibria can exist in a game. Weakly dominated strategies can be played in a Nash equilibria. And in a Nash equilibria, no player can do strictly better by changing their strategy. Okay, so I'm driving this home for a reason. It's a good point to make. With a couple minutes that we have left, here's another game. This is called the investment game. The players are going to be everyone, right, in the room or whatever. Here's the strategy set. You either choose to invest $100 or you choose not to invest $100. Okay? Here's the payoffs. If you choose not to invest, you can just leave. You don't gain or win anything, right? Nothing ventured, nothing gained. So if you choose not to invest, you essentially don't play. If you do choose to invest, here is what happens. If more than 80% of everyone chose to invest, you gain $100. But if fewer than 80 people chose to invest, you lose $100. Okay? This is kind of what investing is. This is why it's called the investment game. If there's a particular stock that everyone wants to buy, the price of that stock typically goes up, right? Because everyone wants it. That's why it's called the investment game. Another example of this, I don't know if people even still use Facebook anymore. I've been off it for so long. But when Facebook first came out in 2007, here's what would happen is you'd get someone would put up a party, an event for a party, and everyone would look to see who was going before they said whether or not they were going, right? Oh, you want to come to this party? Who's going? That is sort of an investment game. Because if everyone just goes to the party, it'll be a great party. But if everyone's like, oh, I don't know who's going, and then no one ends up going, then the party's going to be shit, right? So this sort of thing happens in other places in real life as well, this investment game. But let's look at the properties of this investment game. What is the Nash equilibrium? Again, it could have none, it could have multiple. So can anyone say what a Nash equilibria might be for the investment game? Yep.
I think there are two.
Yep.
The first one is when everybody chooses to invest.
Yep.
And the other one is
There you go. Perfect. Thank you for staying awake and paying attention. That was a great answer. There are two Nash equilibria to this. Like you said, nobody invests and everyone invests. Why is that? Well, let's have a look. I think the easiest way, and again, if you said on an exam, if I asked this, that the Nash equilibria is choosing to invest, that is wrong. The Nash equilibria is when everybody chooses to invest, or nobody chooses to invest. Why? Let's look at the first one. Let's reason about it. Instead of mathematically, let's just use logic. If nobody invests, right? Nobody loses any money. The outcome for everyone is 0. Could any single person have chosen differently to do better? So if everyone else fixes their choice and you chose, okay, I'm going to go from not investing to investing. Well, you're the only person investing now, so you just lost $100. So it's impossible for anyone, any single person, to switch and do better. The other one, everyone invests. If everyone chooses to invest, everyone wins $100. So if we fix the actions of everyone else at investing and choose one person, could they do better by not investing? No, because then instead of winning 100, they just don't win or lose anything. So that's why these two are Nash equilibria. And I'll give you a hint for the exam. Don't shout it out and don't say anything here. Think about what a Nash equilibrium could be for the numbers game that we played in class. Okay, I'm not going to give you the answer to that. Try not to go out and Google it, but there may be a mark or two on the exam related to that. It's an interesting question. So given possible exam questions, given a payoff matrix, compute dominated or dominating strategies, explain why a choice of a strategy is good or bad for a given matrix, compute the best response to a given strategy, construct matrix payoffs so that a given strategy dominates another, definition of Nash equilibrium, both the mathematical one and the English definition, calculate the Nash equilibria for a matrix, and explain the Nash equilibria. If I explain a game to you, you would have to think about it and say what the Nash equilibria would be.